Hi everyone and welcome to a new video about analog electronics. We continue with the inverting amplifier using op-amp, and this will be our first example. Of course we will look at the calculation, also verify these in our SPICE simulations. We have seen in the previous example specifically the voltage follower. Now we will move on and use the theory there and also use a more complex circuit here. So let's look at our example. What we have is the following electronic circuit. We have this circuit given here, again the triangle, which is our ideal op-amp, which is ideal here. And we have R1, R2 and also the load. The resistors are shown here. And we have also the Vs, which is our DC voltage source of 2 volts. We would like to calculate the voltage gain, which is from the source to the load. That is actually this voltage at the load. So the transfer, and also we would like to know what the load voltage itself is. And in the question C, we would like to know what the current delivered by the op-amp is. This is actually this current. So we have a couple of questions here. So let's look at the solutions. Before we move on, of course, we would like to know what the condition is for this circuit. In this case, we have a negative feedback. So we can say, before we move on, let's also recognize that. And we have the two nodes here, V plus and a V minus. So due to negative feedback around this op-amp, we have that the V plus, this node voltage, is equal to V minus. That is very important. And since this V plus is grounded, so directly connected to ground, which is then 0, that means the V minus is also 0. So that is important information for later. Now, the ideal op-amp has an infinite input impedance or infinite input resistance. That means then the current entering the op-amp, which is in this direction, I plus, and also this direction, I minus, must be then also 0. That is all in ideal situation. So we can just assume also this. Now, for the voltage gain, which is then the load voltage over the source voltage, all in DC, we need to first write down the circuit equations using Kirchhoff and Ohm's law, etc. So we have discussed this in great detail in the playlist of electric circuits. So first, right now, let's also define the current directions. For R1, I defined this direction, so plus and a minus sign. The current goes from left to right. For R2, I also do the same. So I do plus and a minus, and the current go always from the plus and a minus, so left to right. I also do that for the load. So from this node to the ground, which is IL. Now I can now write down the Kirchhoff voltage law at the input part, which is then Vs is equal to this voltage, I call this V1, plus the voltage at this node, which is then V minus. But we know V minus is equal to V plus, and since V plus was 0, this is also 0. So this is gone. That means actually this part can be then written as Vs is equal to V1, and using Ohm's law for V1 is I1 times R1, so which is the current times its resistance. So we have now this expression, Vs is equal to I1 times R1. Now, voltage law of Kirchhoff then at the output nodes, actually making this loop, so actually going in this format, so counterclockwise, we have now actually this. So we can say this node voltage is equal to this voltage, of course reversed, because we look at from minus to plus here, minus V2, plus this node voltage also, that is V minus. And again, the same thing, because V minus is 0, we can say VL is equal to V minus V2. And we'll again use here Ohm's law. We can say minus V2 is minus I2 times R2. Again, current times the resistor. So we have now two equations, Vs and also the VL, expressed in current and the resistor. Now we can now set up the equation of Kirchhoff for current. So Kirchhoff's current law, KCL, but at node P, which is actually shown here. So now if we set up the equation of Kirchhoff current law at node P, we can then say I1 is entering this node and it will split in I2 and I minus. But we know I minus is 0 because the current flowing into the terminals of the op-amps are 0 because the input impedance of the op-amp is infinite. So we have, in theory, let's say, in ideal case, an open circuit there. So we can say, get rid of this part. We have now I1 is equal to I2. That is the condition we now get from the Kirchhoff current law at node P. Then we have the following situation. If I now say, okay, the voltage gain was V load over V source, that's shown here, then is equal to minus I2O I2R2. So you just substitute the values, the expressions here for the VL and the VS, and I1 times R1. But we know that I1 is equal to I2. Then we can use this information to say this is also I1. So we have it there. And then you can now divide this out. And you will get minus R2 over R1. That is the expression we actually needed for this equation, the question A actually. So we have it. And we can also calculate it because we know the values 40 and 10 for the R1 and R2. So it's actually a really simple equation. So in order to calculate the gain of this operational amplifier circuit, you just use these two values R1, R2 and R1, not the load, and you have this value, which is then minus 4. So it is inverting. That's actually also the negative sign here. All right, let's then look at the next question, which is then the load voltage. Now, since we know the gain, the voltage gain, we can say, okay, this VL over VS was minus 4, so we can say VS is then, just write it down, times V4, so minus 4 times VS, it's shown here. Now, VS is given 2 volts, that's then minus 4 times 2, and you will get minus 8. So you can see we apply a positive input voltage, VS, it's plus 2 volts, but you get negative input at the output node, which is the load, which is the minus 8 volts. That's actually again the inverting action of this circuit. Now, the final one, which is the current delivered by the op-amp, it's shown here. And again, we can now say, let's then set up also the Kirchhoff current law here at this node, which is the output. We see the load here is created by the I2 and I operational amplifier, OP. So these two together make the IL. That's actually shown here. Now we can say then, in order to calculate or determine the IOP, which is then the op-amp current delivered, which is then load current minus the current through the resistor R2. Now load current and also the I2 can be expressed in voltages and resistors. Now it's shown here. The load current is just VL over RL, and this I2 is the minus of this VL because the actual orientation is from the left to right. So if I measure the load voltage here at this node, then it must be inverted because I see first the minus. It is the minus VL over the R2, and this node is virtually ground. That's why we can say it is this. Now if I now substitute the values for VL, which is minus 8, and it will be then minus 8, it will be plus 8, 50 for our load resistance, and also the R2 was 40. So I will get minus 360 milliamps. And you can again see it is a negative current that will also create a negative voltage. Alright, now let's now move on and collect all the information we have for A, B and C. So you can see all of them are shown here. Now let's now go to simulation results. This is the circuit I have prepared in this SPICE. You can see the values R1, R2 load and op-amp. This is an ideal op-amp, so there are no non-ideal effects. The VS is 2 volts here, and you can see when we add a meter here, current meter, amp meter, and so voltmeter here as the voltage node, we can see directly the calculations we have made here and all verified in the simulation. What we also can do, we can see that in a table form. So this is another form, so we can see the nodes already assigned by the simulators. This is the 0, the ground, 4 here, 1 and 2, so all of them are assigned. You can see the following interesting thing. VP1, which is actually this node 1 or P node, is VP1 is very small value. This is also, let's say, the reason for saying this node P is exactly equal to 0. It is not exactly equal. You can see it is virtually ground actually, because it is not connected physically to a ground connection, but it is really small. You can see minus 2.22 times 10 to the power minus 16 volts. Now you can say it's almost 0. Now this is truly again a proof that this node P is equal to that node. So due to feedback, the op-amp tries to make this non-inverting input and inverting input equal to each other. And the difference in these two nodes, between these two nodes, is almost 0 volts. Now you can see also that the operational amplifier current here is again minus 360 milliamps. So you can see a lot of information here. So a lot of information. Also the load voltage is -8, so also the current. So everything is actually shown here. More information you can see actually in the table. So everything is fine. So we have verified now our calculations also in this SPICE simulations. Let's now also jump to this actual SPICE simulator and also discuss the situation there. And we can also show you how you can generate this table and also make these values there. So let's now jump to the SPICE simulator. Alright guys, we are now in the SPICE simulator for our example about the inverting amplifier. You can see the resistor R1, R2 and the load, 50 ohms. And we have the VS of 2 volts and this is the current arrow. You can find it here, meter, and a current arrow. If you click on it, you can give it a name. And that will measure then the current in this branch. And this will be a pin, that is a voltage pin. It's actually shown here, or voltage node. And it will then give you, if you click on it, it will give you the voltage at this node with respect to ground. Now let's do that. Analysis, DC analysis, and going to the node voltages. And that means actually everything actually which you have put in here as a meter, which you see is exactly -360 milliamps as calculated, and also the -8. You can also click on this. You can directly see its voltage and also its associated current. So it will be highlighted in red. Now what we also want is the table. So you can again go to analysis, DC analysis, because everything is DC, and go to table of results. Now you get a lot of information. Now let's put it here, and you get it here. Now if I click on this one again, you can see it is highlighted for this specific component. And if I go here, for example, it's also highlighted, and for example also here. What you also see here is actually, if I click on this one, this component, I mean this one, R1 is 200 milliamps for this current, and if I click on this, it's also 200 milliamps. So that means there is no current flow in this op-amp. So if this is 200 milliamps and this also, so 200 is equal to 200 plus something, that must be 0. So mathematically, this must be, of course, 0. So this is also a proof that this is indeed, there's no current flow in the ideal op-amp input terminals. Anything else is again shown here, -8 volts, and also the current flow here in here. And this is also shown here in the table. So, alright guys, this is then for this example. The first example actually about the inverting amplifier circuit. I will also discuss a little bit more complex circuit using a T-network, which is also very helpful, where you want to have a large gain but still small values. Because if you want to, let's say, have 100 times a gain or 10,000 times a gain or 1,000, and if this is, let's say, 1K and you want 1,000 as a gain, then this must be 1 million. It could be a problem due to noise and other problems. That is, of course, a little bit advanced topic. And then we will see how we can still get that gain, but then relatively small values in total for the resistors. Alright guys, this is for this example. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for this interesting topic. See you next time in another video. Take care.